Alright, time to get started. Yes, it is.
What you mean? What you do? Oh, wait, it's hard to go with
Hey, we talking about math?
yeah. Where?
Texting that man back?
Oh, dang, dude, you off. How you gonna say it out loud?
Good, y'all stop being ticked. Alright. So, we got several answers here for. Hey.
Alright, my name is Ken. I'm sorry.
So, I need y'all to remember, we have a test on Friday. We gotta pay attention, we gotta move quickly over the next 3 days. So, how many candies do you predict a 165 centimeter tall person could grab? I see several people at 20 and 21, and then a little bit of variability after that. Let's look at it all together. Would someone who said 20 or 21 care to share how they got that 20 or 21?
Because when a trend line helps you predict, your answer. But when you look.
Oh, let's focus on that detail. Remember, the whole point of this trend line is that it is approximating those data points, correct? Mm-hmm. Which allows you to make a prediction off of that trend line. Continue from there.
So when you find 165 or where the height at, would be right in the middle?
So it might be right here in the middle?
Yeah. And you go up to like where the trend line, it stops like right there. Above 165 between 20 and 22.
Interesting. What do y'all think about that?
Yup.
Does that make sense? Okay. Please notice, are there any data points right there? No.
So
But it's a prediction, right? Do we even have someone that looks like they're about 165 centimeters tall?
Yeah.
Yes, right here. But is that what we predict that person to be?
That's what we know.
That's what that person grabs. So please understand what we're doing is we're trying to predict. Now, Caroline had a slightly different strategy. What were you saying that we should do here?
I just put the 165 in and substitute it.
What do y'all think about that? Could we substitute 165 in for x?
Mm-hmm.
Notice literally height is in the place of which variable? X. And so if we do f of 165, and I need everyone to pay attention to this because this is a detail that a lot of students misunderstand and will affect you in math. When we say f1 of x, that's really just the same thing as y. So what is the point of saying f of x instead of just y?
Because the function of x?
It is the function of x, but you can see that it's a function when you just have a y there.
But we're specifically focused on the x, right?
Yes, but also notice how the 165 is taking the place of what? X. So by using this function notation, you can show what your input is while you're trying to figure out your output. Okay? This function notation is not saying f times x, it's not saying f times 165, it's saying f of 165. So I'm substituting 165 in for x. Okay? Now, did anybody try going to a separate calculator page to figure out what this is equal to? Or do the, what am I trying to say? Trying to do a scratch pad page. It's kind of a pain in the butt because you have to remember that entire equation unless you write it down. So I'm going to show you a quick way that you can use later today to help you out. But what were you saying, Caroline? What was the answer here?
I think it was 20.85.
20.85? Looking at what we have here, does 20.85 make sense? It does, doesn't it? Now, I assume you had to go to a scratch pad page and do the calculations that way, correct? Would it be nicer if we didn't have to go through all of that and remember exactly what that equation is on our own? Okay, so here's what I need everyone to do. Pick up a calculator, add a new page in. Oh, I deleted it, didn't I?
Yep.
Hold on one second. I'm going to redistribute. So you should be getting it back any second now. Does everyone have it back? Okay. So create a new page. Anyone want to help Karen out? Remember how to create a new page?
Control.
Control doc, right? That's where it has that plus page. Add a calculator page, okay? Now, don't change anything, just leave the calculator page here for now, but I want you to notice this. Do you see how f1 of x is equal to this? That's defined in the page right here. We good with that? So go into your calculator page. Type f. Notice how, actually I gotta click on it. See how that f right now is italicized? Okay? That means it's not a variable yet that I've used, but as soon as I type a 1, what happens?
It's
It's bolded now, okay? F1, the calculator remembers the function that you defined on the graphs page. What is the input? So I'm going to put parentheses. What was the input again?
165.
165 centimeters tall, right? Hit enter, and oh,
Also calculate the edge mark.
did the calculations for you.
Oh, it's 21.
Well, that's because of rounding. I probably rounded these numbers when it showed those numbers rounded when it's not supposed to be rounded. So yeah, your answer is fine. But I want you to notice, can that be a little bit quicker and more efficient? As long as you understand function notation, you just have to type out f1 of whatever the variable is. Now, you have to be careful about which function it is, because there's f2, there's f3, there's f4, and so you have to pay attention to which equation that it's saved as. All right? Do we see how this could be more powerful or help us in those calculations components? Okay, so, good. So let's look at 1.2 for, I guess it'd be 1.3 now for y'all. So in the previous question, the trend line was f1 of x equals 0.45x minus 53.44. That approximated the data points. What does the 0.45 in this equation represent? What does the 0.45 in this equation represent? I at least heard one person say a correct idea.
Slope.
Slope, thank you. Right? We need to recognize that it is slope, which actual value, slope, amount of candy, slope. Alright. Okay? So, we're talking about slope here. How do we know that 0.45 is my slope? Y equals,
Go back and multiply by x.
let's actually talk about that. Because here's the important thing. It depends on how you approach it. One of the ways that I taught my students last year to do it was y equals a plus bx. What is the slope in this second equation? The b is. Why is the b here my slope, but the m up here is my slope? It's being multiplied by the x. We need to recognize that slope is being multiplied. Why is that? Say it one more time. So we're repeatedly adding, right? Because what type of rate of change?
A negative.
So the rate of change for a line is always what type of rate of change? What did you just say that multiplication is? Repeated addition, right? So this rate of change for the line is a constant, hopefully you've heard that word before, additive rate of change. That slope there is a constant additive rate of change. That's why it's being multiplied. That's one of the big reasons why I focus on multiplication within our first unit, because we have to understand that multiplication is repeated addition. And that defines a lot that's going on here. Now, let's go a little bit beyond that. You will want to take some notes on what I'm about to go over with you, because this will matter today. Okay? So, I want you to notice two things about the equations I've written. Right? These two equations are the same. I'll explain why in just a second. And in a minute, we're going to get more into the slope. What is different about the top equation than you've ever seen before?
The Y?
What about that y?
Square.
It's got a thing on top of it. This right here is read as y hat.
Oh, Lord.
Okay? Literally read as y hat. There is a reason why I put a hat on it. Please remember, and Caroline talked, was it Caroline? I think it was Anaya said this earlier. What is that green line doing for the data? It is a trend line, so it's helping us what? Predict. This hat here indicates the trend line, which we'll use another term for that today, known as a regression line. Predicts the data values. Okay? You have probably never seen that hat before because you're just used to straight up functions where it's y equals or f of x equals. But notice we are making a prediction about what?
The man candies in there?
The number of candies grabbed. Notice how I wrote it here as candies hat, right? Because what is that y really? Candies. You can use the actual variable as a part of the equation. Same thing here with height. Now, the height is not a predictor. We're using the height to predict the candies. That's why there's no hat on it. But whenever you see that y hat, what we are saying is we have some kind of regression function that is making a prediction. Anytime you see that hat in a statistical sense, I have a regression function that is making a prediction. Okay? We good on that hat there? So anytime you make a trend line or a regression function, what do you need to put above your output, your dependent variable? A hat. Got to put that there to indicate that it is a prediction function. Now this next detail is to help us understand linear functions a little bit better. Most of us already said that 0.45 is my what? Slope. What symbol do we usually use for slope? What symbol do we usually use for slope? Is it the mx that's the slope?
Oh, that's the
Remember, the m is being multiplied, which is why that's my slope. It's my constant additive rate of change. Okay? Stop here. It's just the m that is my slope. It's the multiplication by m that tells me that's the constant additive rate of change. So m is my slope. How do we calculate slope? Okay, one thing I do want you to work on. What does this bar right here actually mean? Division. So it's rise divided by run.
Oh.
Right? It's rise divided by run. It's a ratio, division ratio. So, what's my rise then based on the slope that we see right here?
0.45.
0.45. What's my run?
53.44.
Is that negative 50%?
What do y'all think about that?
I mean, should it be negative?
Well, my bigger question is that part of the slope?
No.
So does that need to be the run?
No.
No. The 160, wait.
What's understood to be dividing this, okay,
I thought you meant like
we good with that idea?
the
So we need to recognize, when we have just 0.45, it's understood to be divided by 1, there's my rise and there's my run. So that means I'm going up how far?
0.45.
0.45, how far am I going to the right?
1.
1. But what does this number actually mean in context of this problem? 0.45 what?
That's how you create the trend
Yes, but 0.45 what? 1 what? Okay, let's clarify, let's rewrite or reword this then. Rise, which variable am I talking about when I rise?
line?
The height. Really?
No, the candies.
The candies, which,
Your Y.
the y, right? Rise is always my y, which in this case is candies, which that's what I am predicting. The 1 here then would be my x, or the height. So, for every 1 centimeter increase in height, why is it an increase in centimeter in height?
Because it's positive.
Okay, so for every 1 centimeter increase in height, what's happening?
You add
How much candy?
a 1, wait, 0.45.
That's what we want to recognize. For that 1 centimeter in height, we expect the number of candies to increase by,
0.45.
notice how I said that we expect or we predict the candies to increase by 0.45. Why do we say predict there?
Because we don't actually know the value.
It's a guess. Remember, this whole trend line is just a
Prediction.
It's a prediction, an estimate, a guess. We all good with that idea? Sorry you feel that way. So, we need to understand how to interpret the slope. The slope matters. Yo, Bree. If you're going to fall asleep, don't do that on my calculator. I can't have you drooling all over that calculator.
I was laughing.
You should tell that to your quiz yesterday. So, the rate of change is constant additive. We are saying that if we increase in 1 centimeter in height, we're expecting it to increase 0.45 candies. And so we can actually see that here. Let's just estimate that this is 1 centimeter in height. How many candies is this going up then?
0.45.
So this would be about 0.45. Now, doesn't make a whole lot of sense to look at 1 centimeter in height change. What about if it was 10 centimeters different in height? So that would be, here's about 10 centimeters. There's 10 centimeters. About how much of a change in the number of candies would that be?
You gotta multiply.
It's 0.45 candies
Divided by
for every 1 centimeter. So if I have 10 centimeters, how many candies is that? Multiplied by how much? 10. So how many candies?
Wait,
10.45.
10 times 0.45.
4.5.
Thank you. I did not. I thought you said something else. So 4.5 candies. So notice how we're adding 4.5 candies for every 10 centimeters, right? So if I go another 10 centimeters, how many candies am I expecting it to add?
I was not gonna say
4.5. If I go another 10 centimeters, how many candies do we expect to add? Another 4.5. This is what we mean by a linear function or a linear relationship, is that we just expect it overall to constantly add. All right? Notice, is the data a line?
No.
No. That data is not a line. If it was a line, it would fit perfectly on this green thing. Is that data a line?
No.
No. Is the data linear?
Yes,
What's the difference?
because a line is, I think linear, it can create a line, but it's not gonna necessarily be a straight line.
And a line is always straight. Linear just
Well, it
means
doesn't
a
have to be
general
straight.
shape. Linear just means, is it like a line?
Yeah.
Yes. The general shape of that thing is a line. It's not a perfect line, but the general shape is a line. Okay, I will leave this up here so that you can use this in the beginning of the task today. So don't forget, we briefly looked at these objectives yesterday. We want to be able to interpret the residual of a data point and a trend line, which that trend line is known as a regression line in your task today. We want to explain what makes a trend line a good approximation of bivariate data and use that to explain why the least squares regression line is the best trend line for a bivariate data set. And then this whole extrapolation, interpolation. So, we didn't talk about this at all, did we, yesterday?
Well, wait.
The number one here? I know y'all graphed the data yesterday, correct? I don't have it.
Wait,
Did I collect the file for y'all, or did I leave it on your calculators?
I think you collected it before we left.
Check your calculator, go to browse, and see if it's still there.
Oh my goodness.
What is it again, Miss Kim?
It was called Squared Up.
No, I
So
see.
browse your calculator, go to third block.
Yes. I got to go square it up.
Yeah.
You're hurting my head.
Huh?
Square it up.
Square it up. Is that there?
Yeah, mine. Well, I think it's. Yeah, wait, this, yes.
Yeah, I never collected Squared Up. If you were not here yesterday, then you probably did not get a copy of it, so let me send it to you. Alright, so Kyron wasn't here. Who else wasn't here? Maven? Don't have it?
Don't have.
The calculator file? Does anyone else not have any calculator file on their calculator? That means we should have, it should still be on there. Anybody else? Alright. Those of y'all should have it now. So, what is wrong with you right now?
I'm in a good. I could be asleep right now.
That's true, you could be asleep. Alright,
I'm about to be.
so, Squared Up is what we're working on. This, dang it, I forgot to bring this up earlier. Really quickly, I need y'all to notice this from the warm-up. This is a trend line or a regression line, correct? Is it the only possible trend line?
No.
No.
It's
We
one
talked.
going like to the side, and it's one going the other way.
That could be a trend line, correct? What about this?
Yes, we're just looking for the best ones.
Okay, and that's what we talked about yesterday. There are lots of trend lines possible. The best one is what we are looking for today. It is something known as a least squares regression line. And so with Squared Up, here is the data that you will be using. Please be aware, on the years, we have 1900, 1910, 1920, 30, 40, all the way up to 2000, and then we have every year from 2000 to 2004. That will matter in a little bit. We are going to just focus on these numbers right here, though. What are these numbers in pink?
How did you get there?
Just people in general.
But what is it about this?
The average.
The average what? Life expectancy, right? So it is the average life expectancy. So in 2000, every person in the U.S. could expect to live how long? 77 years on average, right?
How did you get
Huh?
Yep, second page.
You didn't open the document.
There was no document for me to open.
Yes, it's still there from yesterday.
I don't think so.
I think it is. You didn't look.
I'm looking
I know.
Oh, there it is.
Okay. So, we have our pink data about just people in general. Now, this is where we want to move into number 1. So what did we need to do yesterday to graph this scatter plot?
You had to press menu.
Nope.
Miss Kim, that's literally what the paper said. Where you on the front back?
It doesn't say anything about menu on number 1.
Miss Kim, what did you?
Oh, because adding a variable.
Oh.
So,
Okay.
Create a scatter plot.
we already did that, next.
But not everyone was here yesterday. So for those of y'all who don't already have this scatter plot created, so I do want to point this out. In the past, I made y'all make the scatter plot in a graphs page. This is not a graphs page. What page is this?
Data and statistics.
Data and statistics. Look, if you were to create a new page, what page would line up with this? Data and statistics, okay? That's what I'm trying to get you to see. So for those of y'all that were gone yesterday, we should be on 1.3. Don't just grab this paper, I need you following along. What do I need to do to create the scatter plot? Click to add a variable. Which variable should go on the x-axis? If you look at the sheet, it tells you.
Year.
The year. What would be on the y-axis? Person, right? Because we are just looking at how, listen, we're just looking at how the age or life expectancy of people changed over those years. Notice the year is explaining those average life expectancies. Maybe can you grab the door for Brianna? So, the final thing I want to point out before I release you all is looking at number 1, it says describe the relationship between the two variables. No, before I release you to work within your groups. Okay? So, how would you describe this relationship?
As the years go by,
Oh, now I was talking, and then I'll let y'all add on. You started talking over somebody else. You can't get upset. As the years go by, what did I?
the life expectancy rises.
The life expectancy rises. Does anyone want to add anything to that? That's it?
Perfect.
That's perfect?
Yeah,
It's still increasing in there. We are missing an important detail. Y'all, yes, as the years go by, the life expectancy rises. However,
The slope is positive.
so say again.
The slope is positive.
Okay, the slope is positive. Now, is this a perfect line?
It's
No.
through 2 dots.
Okay, but so we say it's what?
It's linear.
Thank you. Right? As the years go by, the life expectancy rises. That means it does have a positive slope, but it also means that we are looking at a linear set of data.
I said that, just like correct.
And the data is fairly linear. We will learn how to evaluate how linear that data is at the end of class today, but we need to get moving somewhat quickly. So as the years go by, the life expectancy rises and the data is fairly linear. You cannot do a trend line if the data is not linear, right? If I had data that looks like this, would it make sense to put a line through that data?
No.
No, because that's not what? It's not linear.
Wasn't there a name for that?
Yes,
I forgot.
exponential.
That was like what I was talking about. But
Okay, at this point, move to the gray box, follow the directions where it says add the movable line. It tells you exactly what to do. I'll come around and check on you. Once you add the gray box, move on, or once you follow the gray box, move to the back side of this page. Okay? So follow the directions. Work with each other if anyone's stuck.
I said like 3 times.
Okay, Tristan needs to say it, and I need to acknowledge that too.
I don't know, you just have started.
Sure, that's what it is.
What you want, a juice box?
On my back. Hold on, I'm gonna.
If a juice box don't make you feel better.
Where's that? Yeah, we just.
I already ate my food.
There you go, Tristan.
Ow! Oh my.
Okay, Miss Kenny, I think you're right.
Talk about your
I
gray
think
box.
you said
Gray
my
box,
back.
they don't know. Gray box. Excuse you, $50 just to get the volume.
Got my line.
Yeah, you got your own.
Yeah, put me.
Hey,
Soft.
okay,
That's so good. You gotta go through that. You gotta go through that.
Oh, the line. Well, 2 points will define a line, but not necessarily that. You want to make the line fit the data as well as possible. But if you have a line that you think hits the data pretty well, then move on to the back of the second page. It'll help you understand.
Were you out of the movable line?
Oh, hey, really quick question. Has everyone got the movable line in there?
Yes.
Okay, so I need you all to watch this because some students missed this detail earlier. So when you add your movable line, there are 2 ways to move this line in 2 different directions. If you move your cursor to the middle of that line, what pops up?
The,
The 4-way arrows. Okay? So if you go to the middle, 4-way arrows, if you click and hold, you can now move the line up and down. Okay? If you go to one of the ends, what does it give you? A little circle. And what's that going to do?
they go like, the same way. What a different direction.
So is it moving up and down though?
No,
It's rotating it. Okay? And I will point this out, and this is important. What is changing when I rotate it? The slope and the y-intercept a little bit. But when I move it up and down, what is moving?
The y-intercept.
Just the y-intercept. So you need to use both the middle and the ends to move it around for the next part. If we know how to move that line around, you should move on to the next part, which is talking about residuals. Okay? So, to give you some background, look at the back of the first page. Look at the back.